Good afternoon and welcome to this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor. My role today is to introduce the topic and the software and then hand over to our esteemed guests. Now, today's webinar is in partnership with Oxford Instruments, who've helped us not only identify an important and interesting topic, but also find the right people to talk to you about it. So today we're going to see how X-Pulse benchtop NMR enables you to develop a deeper understanding of your flow chemistry. Over the course of the next hour, we'll learn how multinuclear benchtop NMR can assist your understanding of reactions, how the flow cell integrates with existing pulsar and X-Pulse instrumentation to enable continuous flow sampling. We'll learn about some of the reactions that can be monitored and the thermodynamic data that can be obtained, and we'll also learn about the stability that the flow cell offers in order to obtain 1D and 2D NMR data. So there's a lot coming up in the next hour, and we're delighted to welcome James Sagar and Ryan Buis with us. Now, we'll be hearing from James first. He is Strategic Product Manager at Oxford Instruments. He's been there since January 2019. He joined Oxford Instruments way back in 2015 after doing his postdoc at UCL, that's University College London. Ryan, who we'll then hear from shortly afterwards, is a senior lecturer in inorganic chemistry at Manchester Metropolitan University. He got an MChem and PhD from the University of Hull in 2005 and 2009, and then did postdoctoral research at the University of York. In 2015, he joined Manchester Metropolitan University in his current role as a lecturer in inorganic chemistry, currently senior lecturer. So we're delighted to have them with us, and we would like to say a big thank you to Oxford Instruments for putting us in touch and working with us to develop this content. Now, we're using GoToWebinar to deliver today's presentation, so you should see a strip on the side of your screen that allows you to control your own GoToWebinar experience. Now, the most important bit of that from our perspective is that there is a box where you can ask us any questions. So if any questions occur to you at any point throughout the presentation, just drop them into that box, we'll pick them up and we'll be able to put them to our speakers at the end of the presentation. It's possible we'll run out of time, in which case the GoToWebinar platform really comes into its own, because not only will we have a record of all of your questions that we can send on to our speakers. If they're able to send you an answer, they'll be happy to do that after the webinar, but also the entire thing is being recorded. So if there's anything you miss or anything that you would like to go through again, then you'll be able to come back and watch this recording at your leisure as many times as you feel necessary. So I think that's quite enough from me. Do use that questions box as we go through, but the important bit now is to get to the real content. So I'm going to hand over to James, who hopefully will be the next voice you hear, and we will see his presentation. And then I can take a back seat while we talk about understanding your reactions in more detail with benchtop NMR. James, thank you ever so much for joining us.
Thank you, Ben, for that kind introduction. As Ben said, today we're going to talk about how benchtop NMR can help you understand your reaction chemistry. Initially, I will give you a brief overview of the technology of benchtop NMR, and then I will hand over to Ryan, who will talk through the experiments that he's been doing with flow NMR and monitoring reactions. So what I'm going to discuss today is where benchtop NMR has come from in the last 7 or 8 years since these systems have been available, where we are now in terms of the technology, what you can do with broadband NMR on the benchtop, and then I'll hand over to Ryan to talk about the flow NMR that he's been working on. So where's benchtop NMR come from? And this is a very, very brief history. So about 8 years ago, the first benchtop instruments started to appear, and these instruments were capable of taking simple 1D proton spectra like this ethyl crotonate spectrum here, where you have all the same information that you would have on a typical high field 600 megahertz system, but it could be harder to get at because you don't have the spectral dispersion that you would have at that high field, and also you didn't necessarily have the resolution, so you end up with a lot of overlaps in the spectrum that can be hard to deconvolute. But then the technology started to develop, and we started to add in things like two-dimensional experiments, both homonuclear and heteronuclear, so you start to be able to pick out some of the information that was there hidden by those overlaps. And then you started to add things like an X channel for most systems, whether that was a 13 carbon or a 31 phosphorus. So you can start to look at heteronuclear correlation experiments like this multiple editor HSQC on the left here. So that gives you not just the information about the correlations between the proton and the carbon, but also the understanding of the CH2, the CH3, and the CH groups. As well as these technological advancements, we also started to add things like flow cells to the NMR system to allow people to measure and monitor dynamic experiments. But where are we now? What we're trying to do is develop a whole new level of versatility in your NMR on the benchtop. So we recently launched the world's first broadband benchtop NMR spectrometer. So based on a 60 megahertz permanent magnet, that's one of the real big things with benchtop NMR, is that you don't have to have those cryogens that you would have with high field. So typically the running costs are much lower, and you can also position them much closer to the experiment that you want to understand. We can improve the line shape significantly. I will talk about that in a couple of slides. We make the system flow NMR capable, so that will allow us to collect the data that Ryan will show you. And we can add this broadband X channel, so you can analyze a whole range of different nuclei. We've also added some of the functionality that you might see on a high field system, such as variable temperature and being able to understand reactions not just at a single temperature, but over a range of temperatures. So one of the big things that has improved massively in this generation of benchtop spectrometers is resolution. So from the technical side of this, what we call the magnet homogeneity. So if you have a low homogeneity magnet, all nuclei see a very slightly different external field, which means that when you look at your spectrum, you'll see ever so slightly different chemical shifts, and that results in a broad peak and spectral overlaps, which make the spectrum hard to analyze. What we've done is move to much higher homogeneity. We've put a lot of work into improving the homogeneity so that essentially more or all of the nuclei see exactly the same external field. That means that the peaks are sharper and your spectra are easy to analyze. In real terms, what does that look like? Well, if we take that initial ethyl crotonate spectrum that I showed you at the start, which is still in red here, and compare that with a spectrum taken now on a system like an X-Pulse, you can see the significant improvement in the resolution. So at 7 ppm, you can see the group of peaks there. At the original instrument with a half height line width of 1 hertz, a base of 40 hertz, you essentially have something that looks like a bulge with a couple of peaks on the top. With the improved resolution of new systems, actually all those peaks are resolved and you can get right down to the baseline. But importantly for things like quantitative NMR measurements, if we look at the methyl groups that I've highlighted here, at a base of 40 hertz, the two peaks or sets of peaks overlapped. Even though slightly, it would make quantifying those signals very difficult. Whereas now we get down to the baseline between the peaks, so it's much easier to quantify. That resolution also allows you to do other things. One of those is very, very effective solvent suppression. So here we have a whole set of different metabolites in water, and you can see if you don't use solvent suppression, you essentially have a very, very large water peak, and all the signal that you are collecting from those metabolites is at very low levels and quite difficult to distinguish. Or if it's very close to that solvent peak, it can actually overlap with it and be even harder to distinguish. Whereas because we've got the resolution, we can suppress that solvent peak in a very, very narrow band, so just removing the solvent peak, and you can see the metabolites much more clearly. But what you can see there is that there are still a set of overlapping peaks that can be quite difficult to distinguish. So what can you do in order to improve that further? Well, what you can start to do is things that you might look at on high field systems. So selective excitation. So here we have two compounds in mixture, hexanoic acid in ethanol. And if we look at the spectrum from the mixture at the top in blue, you can see that there are a huge set of peaks, but we don't necessarily know which ones are associated with which molecule, and there are some definite overlaps between peaks from the two molecules. So if we selectively excite the region associated with carbons 3 and 4 on the hexanoic acid, these are using a 1D selective Toxi pulse sequence, we can excite just the spectra associated with the hexanoic acid. And then as well, we could, in a separate experiment, excite just the peaks associated with the ethanol by picking and selectively exciting the region associated with the E2 carbon there on the ethanol. And what that allows us to do is that although many of those peaks were already separated in the top spectrum in blue, the methyl groups were significantly overlapping, and this allows us to separate those out and analyze them independently. And that is a real advantage when it comes to the flexibility and the usability of benchtop NMR for analyzing things in 1D or just with proton. What we can now start to do is think about not just the proton channel, but also the broader X nuclei channel. So the X-pulse system is designed to be versatile and modular. So what we have on the front of the system are these X-pods, which can be changed. So you'll always have your proton X-pod, but then you can insert an extra X-pod that will allow you to access different X nuclei. So whether that's 29 silicon, 13 carbon, 11 boron, or 31 phosphorus, or actually a whole range of X nuclei on a single X-pod, giving you the ability to analyze all nuclei between 29 silicon and 31 phosphorus in frequency. So what are those nuclei? Well, I've picked out a selection here. There are a few more exotic nuclei that I haven't put in here, but what I tried to do here was show you just where those things can be used. So if you're teaching NMR, then you might want to teach your students about proton, fluorine, carbon, phosphorus NMR, which are typically much more widely used. Also, these benchtop systems, because they're lower frequency, tend to have a broader bandwidth, which means that on our system, you could also look at things like paramagnetic and diamagnetic molecules. But these X nuclei then become particularly interesting for certain industrial applications. So pharmaceuticals, you may use your normal teaching set, but also consider looking at platinum NMR for therapeutics, or maybe lithium batteries where you might use your proton and carbon, but also the compounds that they use there where you're dissolving your lithium containing compounds in organic solvent, things like lithium tetrafluoroborate or lithium hexafluorophosphate. You can start to measure the phosphorus and the boron associated with those and quantify it, so you get a much better understanding of your mixtures. And also things like in food and agriculture, you can now measure sodium on the same instrument as carbon and phosphorus, so you can start to think about analyzing things like salt content. What do those spectra look like? Well, if we look at this 7 lithium spectra, these are 4 different lithium battery electrolytes, and actually the spectra are pretty boring. They've only got a single peak in them, but what it does allow you to do is quantify the amount of lithium in your system, and you do start to pick up some chemical shift information. You can see that from the boron spectra, carbon, silicon, phosphorus, we're able to start to pick out real usable information from all these other nuclei other than your typical proton or proton fluorine. So what I'm going to do now is we're going to run a short poll just so I can get a better understanding of what X nuclei you might be interested in, and then we're going to hand over to Ryan to talk you through the work that he's been doing with his Flow NMR system.
Thank you very much for that whistle-stop tour of the history there, and a good introduction to the sort of protons we can use. So the next thing you should see on your screens will be the poll. So this is your opportunity to get involved and let us know which nuclei you are interested in. So we have a good full list there. We've just seen the sorts of things that they can be used for, but I guess what we want to know is, what are people using them for? So we'll give you maybe about a minute or so to get as many answers in as we can, and then we'll have a brief discussion before moving on to Ryan's part of the presentation as well. I can see a few of you have already got some questions in, so I'm really pleased to see that. Glad you're all engaging so much. Do keep them coming as we go. We've had a few really good. A couple of people have had issues with the sound. I'm afraid any online presentation like this, there can be dips in connection speed at one end or the other. So if the sound does drop out for you for any length of time, don't worry, it will come back. And anything you missed, you can once again go back and watch the video to pick up on anything that you may have missed during there. So in particular, Monica, we're really sorry if you have been having sound problems, but it will come back, and do stick around and enjoy the rest of it. So I think we probably just need to give you a few more seconds. I'm watching the results coming in as we go. It's about 70% of you have voted. That's probably going to be enough. So let's stop the poll now, and we'll share those results so we can have a look. So, I mean, the clear winners are those commonly used ones, but it's a reasonably good spread there. We're not looking at anything that is totally absent from the results. Is this kind of what you expected to see?
Yeah, I think that's pretty much exactly what I expected to see. The majority of people will be using proton, carbon, phosphorus, the more common organic nuclei, but it is really interesting to see such a large percentage are so interested in those extra nuclei in the broadband range, where you might be able to do some interesting inorganic chemistry.
I assume they are not as established. They're not as well known. Perhaps the way that people have learnt chemistry as they came up through university, they weren't an option a few years ago. So I guess people are often using what they're familiar with. They know how to use them. They trust the results, and so they know that this is something they can rely on.
Yeah, I think that's exactly right. That it's going to be interesting to see that now this capability is there, what people can actually find uses for it.
And as it becomes more accessible, and the current crop of undergraduates, this will be quite familiar to them. I guess we're more likely to see it coming through in research and in industry.
Yeah, definitely, and I think there are certain industries, especially things like lithium batteries now, that are growing, and the ability to understand more about the compounds in those mixtures that you might have is only going to allow people to do more and more interesting work.
Just before we hand over to Ryan, one quick question that I think may just be a case of the language that we're using. When we're talking about benchtop NMR, we mean that quite literally, don't we? We mean an NMR machine that is literally on the bench in front of you, rather than the very early ones, which required incredibly large cooling systems and so on, and essentially were a room of their own. So Belal has asked us if that's what we mean by benchtop.
Yes, so benchtop NMR literally means on the bench, or in fact, in the case of that Ryan is going to talk about, his instrument is on a trolley that can be easily pushed around the lab to be as close to the reaction that he wants to monitor as possible.
So, Bilal, hopefully that clears up what we mean when we say benchtop. So thank you very much for your question. Okay, I think we've looked at these results for long enough. Thank you to everybody for taking part in the poll. We're now going to hand over to Ryan for the rest of the presentation. So hopefully Ryan Mewis will be the next screen that we see and the next voice that we hear. Ryan, thank you ever so much for joining us.
Hi everybody, hopefully you can all hear me. So I'm going to take you through some of the work I've been doing on the flow NMR system that I've got here at Manchester Metropolitan University. What I'm going to show to you is not an exhaustive list of experiments. I'm hoping it's going to basically stimulate some discussion, get you thinking about what kind of chemistry you could do that utilizes the flow NMR that I'm going to talk to you about. So in terms of actually what we're doing here, you've got a reaction mixture, which is shown on the right, and we're constantly flowing that liquid through the two poles of the magnet so we can interrogate it using radio frequency pulses. And you can see on the left-hand side that we've got some spectra being generated. We can see that the quartet, which is at lower chemical shift, is decreasing in size, whereas that on the left-hand side, which is another quartet, is increasing. And we do this continuously, So we're not doing a stop flow experiment. It makes it very easy to actually automate this process because we don't need to change the pulse sequence that we're using. We can just basically continuously run the same pulse sequence whilst that liquid is flowing around the system. In terms of an experimental setup, we can see that here in terms of the fact on the right hand side, we actually have the reaction vessel that we're looking at. We can see that this has actually got something like a reflux condenser that's attached to it, which is something we'd expect to see. And what we're doing is we're actually sampling the reaction mixture using this line here, and that's being drawn up by a peristaltic pump. Peristaltic pump then pushes that liquid round and towards the magnet where it enters the flow cell. Now the flow cell is basically two glass tubes, one within the other. On the outer side of that is basically the lock fluid. So the lock fluid I've been using here is D2O. That's to enable us to actually shim that system up and also to provide us with a constant lock if we're doing 2D and also sometimes 1D acquisitions. The liquid and the reaction mixture that we're looking at is going down the center line here and we're pushing that upwards. So mechanically that means that if there's any air in that system, we can push it upwards and outwards away from the system, and that prevents any airlocks in the system, which can lead to inhomogeneity in the actual NMR spectrum, which is what James talked to you about in the first part. That liquid then gets returned once it's come out of the flow cell and back into the reaction vessel. And we're going to constantly basically flow that liquid round at a set flow volume, a set flow rate, and can continuously look at it using radio frequency signals so that we can generate our spectrum. So in terms of actually the type of spectra we can generate, here's an example of something I've been looking at. So you can see I've not picked something entirely very complicated here. So I've started off with ethyl ethanoate or ethyl acetate. Those names are very interchangeable. And we've got a spectrum that is representative of this molecule. So this is a single scan proton NMR spectrum. So we're looking at neat ethyl acetate here. And the important thing to actually mention here is that we didn't need to use any deuterated solvents in our reaction mixture. So because we've got that D2O lock contained within the flow cell, we don't need to basically have any deuterated solvent in our reaction mixture. And that's really important because it helps to reduce cost and it also helps us to actually sample an actual real reaction mixture that we want to look at. So down here, we can see we've got the triplet and the quartet of the ethyl group, the CH2 being the most downfield signal here because it's de-shielded by the oxygen. And then we've got the singlet of the methyl group here, which is a singlet because it's got no protons next to it. So this is the methyl group we're looking at here. About 5.25 ppm, we've got the water signal. That water signal comes from the D2O. So we've got some trace amount of water in our D2O that we use for the lock. And we've used D2O in this instance because basically it doesn't actually coalesce or sit on top of the other peaks that we want to look at. So one of the first things I started doing with the system was actually looking at how the flow rate affected the spectral quality. I wanted to do that because in some instances you might want to be monitoring a reaction whereby that proceeds quite quickly, and therefore you need a quicker flow rate in order to investigate it. So this is what I'm showing on this slide here, where we've got just monitoring the actual signal intensity of the CH3 of the eval group or the CH2 of the eval group, and just plotting them as a function of flow rate. And we've got the flow rates here that go from 1 mil per minute up to 10 mils per minute. And we can see there is actually a slight drop off in signal intensity going from the slowest flow rate up to the quickest flow rate. I'm going to show you in the next slide why that is. But in terms of the actual quality of the spectrum that we're getting here, it doesn't really ultimately matter what kind of flow rate we're going to use. We can monitor this at quite quick flow rates, which is actually quite advantageous if we've got a reaction that's proceeding very quickly. So in this next slide, I've just basically taken a sample of those spectra that were used to generate the graphs on the previous slide. We've got 1 mil at the minute, 1 mil per minute at the bottom, up to 10 mils per minute at the top. And in terms of the actual quality of the spectrum, we can see we're not losing any definition in terms of what we're looking at. We can still see this as a triplet up here, a singlet at 2 ppm and a quartet at about 4.1 ppm. What we're just doing here is actually slightly broadening out that peak. And that becomes from the fact we've got such a quick flow rate that we're trying to actually acquire against because we haven't actually slowed down our pulse sequence. And we can see that particularly for the methyl single here, the singlet, it's very sharply resolved here at 1 mil per minute. It's quite broad at 10 mils per minute. Now I've chosen this slide just to show you the spectra as how I've actually obtained them. I haven't done actually any processing aspects on them, and certainly I haven't actually tried to basically make certain spectra look bigger than what they are. These are all basically relative to each other, so we can see the effect of the broadening out when we go to actually the quicker flow rates. But what I wanted just to actually impress upon you is the fact we can still see those signals even at the actual higher end of the flow rate. As well as 1D NMR spectra, I also wanted to have a look at basically getting some 2D NMR data. And again, I'm just basically looking at ethyl acetates again here to generate a very simple proton-proton cozy. And what we can see in this cozy is we've got the expected cross peak, which has shown both sides of the diagonal line, which represent the correlation between the CH2 and the CH3 protons of the ethyl group. The isolated methyl group shows no cross peaks because it is isolated in the spin system. To the right-hand side, I've got the experimental details about how this cozy was collected. So we're using 1024 points in the F2 direction, which is the horizontal, and 128 points in the F1 direction, which is the vertical. And each of those points in the vertical direction was acquired 4 times. We're using 4 scans per time domain increment. Those of you who are familiar with cozy will see that I'm using a 90-degree pulse here. You might be more familiar with using a 45-degree pulse because then it helps basically speed up the experiment in terms of relaxation relative to actually the signal to noise gain. Now, the great advantage of using the flow system is because we're constantly replenishing the liquid in between the actual coils where we're applying the RF. Relaxation becomes something that we don't really have to worry about too much. And this reason I can actually use a 90-degree pulse and a 1 second relaxation delay, because then I've got actually more material that's going to be replenished within the coil, allowing me to build up this 2D acquisition in a far shorter space of time. So this was acquired using a 1 mil per minute flow rate, and it took 12 minutes to acquire this 2D proton-proton cozy spectrum. And I wanted to see how much I could push this now, based on the fact I knew what I could do with the 1D in terms of actually upping the flow rate. And before I did that, I actually started to think about how few time domain points I could get away with in the F1 direction. So I've now halved the number of actual time domain points used in F1, which is the vertical direction, kept the number of scans the same. So I've only changed one variable in terms of collecting this 2D spectrum. And this has taken about 5.5 minutes of acquisition time. We are looking at neat ethyl acetate, so I'm not looking at a reaction here, but I'm just basically showcasing again what we can do in terms of acquiring a 2D spectrum. So again, we have a flow rate of 1 ml per minute, and I wanted to basically see next if I can increase the flow rate, how the actual quality of this proton-proton cozy spectrum be affected by any differences in the flow rate. So that is shown on this slide here. We can see we've lost some kind of resolution in the peaks, but we can still see that we've got the expected 2 cross peaks, one either side of the diagonal, and we can see the actual 3 points of the diagonal line as well. So even though we've actually increased the flow rate by a factor of 10, we've still been able to get a spectrum that explores and explains the actual coupling within this molecule, and it's still only taken 5.5 minutes to acquire. So this was something really I wanted to do because I wanted to see how much this system could be pushed, how much could it be used to monitor reactions that sometimes are quite quick in terms of their reaction speed. So in terms of monitoring reactions, I've talked a lot about ethyl acetate, which is this molecule shown here on the product side. So it's basically formed from acetic acid or ethanoic acid and ethanol in the presence of a few drops of H2SO4 to catalyze it. And what I wanted to do was actually monitor this reaction. For those of you who know a bit about this kind of reaction, you'll know that it actually exists or is formed for various different equilibria. So it's not one that's going to go to completion. It's going to be quite slow and ponderous because there's a lot of reversibility in terms of the reaction proceeding. What we've got down here in terms of the actual spectra are a series of 1D proton NMR spectra that basically show the differences in the reaction matrix. So I'm basically flowing this around the system and interrogating it using radio frequency pulses to see how the actual mixture changes over a period of time. Every spectrum was collected every 2 minutes. So each of these spectra is 2 minutes in terms of a time increment. And we can see initially that the integral area that's shaded in blue, there is none of this material that is actually there. And that is because that is the CH2 that comes from the ethyl chain of ethyl acetate. So at time 0, we don't actually have any of that in our system. The integral area shown here in green is that of the same CH2, but in the ethanol starting material here. So we've got a fairly nice difference in terms of chemical shift, so we can easily integrate these two areas. Those of you who are more eagle-eyed will have noticed that I'm only actually integrating the 2 central portions of each integral. And that's because, given the fact how closely together these 2 quartets are, I didn't want to basically steal any intensity from either 2 quartets when I'm trying to plot the data as a function of time, when we're looking at the integrals and how they decrease or increase from the actual starting time domain point. And that is shown graphically in the top left here, where we've got all these data. So all these are actually different proton NMR spectra, where we've integrated each spectrum and we've plotted it as a function of basically time. And we can see that the blue area, which is that of the actual CH2 in the product, increases, whereas that of the green point, that of the CH2 in the starting material, decreases. And using that, we can actually work out the reaction rate. So we can do that mathematically, such as using a platform such as Microsoft Excel, and we can do that by then extrapolating out and get the reaction rate. So in terms of the volumes that I was using here to monitor this reaction, I was using 10 mils of ethanol and 10 mils of acetic acid, and these are effectively molar equivalents. So I'm basically taking 1-to-1 equivalents of both of my starting materials, few drops of H2SO4 and letting them react, and then just monitoring the reaction using the setup. The good thing about measuring reaction rates is we can actually use that to get some kind of thermodynamic data relating to a reaction. So I want to actually be able to showcase to you that we can use this NMR data to gain some actual insight into the reaction that's taking place. So what we can do here is we start off with the reactants. We can actually work out the thermodynamic values associated with going from the reactants to the transition state. for the reaction of taking acetic acid with ethanol to form ethyl acetate. And we can do that by using the Eyring-Polanyi equation, which is shown here at the bottom of the slide. So this is in the format of y equals mx plus c, where we can see that if we plot natural logarithm of k over t against 1 over the temperature, then the gradient will actually give us the value of delta H, and the intercept contains the value of delta S. So delta H and delta S are enthalpy and entropy respectively. And if we know both of those values, then we can calculate the Gibbs free energy associated with going from the reactants to the transition state. In practice, what we need to do is do the same reaction using the same amounts at different temperatures. And because we're looking at a reaction whereby I've got a round bottom flask, maybe fitted with a reflux condenser, underneath it I'll have a stirrer hot plate, so I can easily modulate the temperature, monitor that using a thermometer, and basically make sure that I've got good control over my system. So this is what I did. I looked at a temperature range that started off at 22 degrees up to 72, so we've got a temperature range there of 50 degrees, and I worked out the rates by basically taking that data that we get from the series of proton NMR spectra and working out the rate associated with them. And that we can plot the graph shown on the left, whereby we've got a series of points, and it should adopt a straight line because it's in the Eyring-Polanyi equation is in the format of y equals mx plus c. And I was very happy with this in terms of the agreement, in terms of how well those points fit along the line of best fit. And from that, I was able to get these thermodynamic values out in terms of the enthalpy, entropy, and delta G. I won't spend time reading those out. They're there for you to see on the screen. Just bear in mind, this is for the reactants going up to the transition state. So the enthalpy, entropy, and Gibbs free energy there are not for the reaction. They're only for the reactants going up to the transition state. So something I could do in the future is actually do the reverse of the esterification reaction, whereby I take the ethyl acetate that I've produced, I hydrolyze it, I break it apart into its respective components of acetic acid and ethanol, and then actually get a different set of thermodynamic values. And once I've got both of those values, then I can actually calculate the values for the actual reaction. So that is something I'd like to do. And the reason why I'd like to do that is because it supports very nicely an undergraduate program in chemistry, whereby it's showing the students how organic chemistry can be mapped on top of actual physical chemistry using analytical techniques. So there's a lot of different variables there in terms of them thinking about this kind of coerced effort in terms of what their chemistry degree is about. So everything I've shown you so far has been about proton, which is good because in the poll, that was the most important nucleus that came out of that. I'm going to now show you some fluorine, which was a little bit lower down the list, but still something I think is very important to look at, particularly in the pharmaceutical trade. About, I think it's 60 to 70% of most drugs have got a fluorine in there somewhere. So it's quite an interesting point industrially to actually monitor things using fluorine. And the great thing about fluorine is it's substantially better chemical shift window. We take away the fact that these peaks have a much lower tendency to overlap because we've got a much bigger chemical shift window to look at our peaks. So we notice the reaction that we're looking at is very similar to what we did before. The only difference is the fact that we've now got a CF3 group on the ethanol instead of where we used to have a CH3 group. And the spectra shown at the bottom are a series of 19F or fluorine 19 spectra, and they have been collected every 5 minutes. So in terms of the actual total acquisition here, we've got over 10 hours of acquisition. And there was two things I wanted to achieve here when we did this experiment. Was one, to really show the actual fact we could use fluorine in the same way as proton, but it has some significant advantages, which is based on the fact that these peaks are nicely separated in terms of their chemical shift. But also two, how did the instrument respond to actually acquiring data over that time period in terms of stability? So if we look at the actual data we've got here, the eagle-eyed amongst you will notice there is actually some material in terms of the product. This is the CF3 group of the ester, shaded in kind of like a beigey cream color. And that was because I'd already done some experiments already with this reaction mixture. I wasn't really starting from time zero. And that was because I was really kind of probing how quickly this reaction proceeded prior to me collecting all this data, because I'm doing it actually at a reasonably cold temperature of only 18 degrees. So this isn't basically the reaction proceeded very quickly at the start and then died off. It was because I'd already started looking at it. The peak that's shaded in red is the CF3 group of ethanol here. So this is the 2,2,2-trifluoroethanol. That's the starting reagent. And again, I can plot this data. It's a series of points, and we can see the reason why we probably want to do this over a period of 10 hours. And that's because it's very, very slow. So if I was only looking at 1 hour of acquisition, I'd be hard pressed to actually see if the reaction was actually proceeding or not. Whereas if I do it over this longer period of time, it's very clear that it is actually moving forwards. So on the next slide, I've got 2 fluorine spectra, one which was collected right at the start of that 10-hour period, and one that was actually collected right at the end. I just wanted to show these as a kind of blown up spectrum, just to show about the differences in terms of that quality of the spectrum. Just worth bearing in mind that I haven't shimmed in between the actual 2 spectra that are being collected here. So they were shimmed right at the start and then basically left to go for 10 hours. So the only thing that we can really see here is the difference in terms of the actual quality, or the intensity, sorry, of the peak that is actually at higher chemical shift. And that is because that peak has been produced. Whereas if we actually looked at this peak as well in a little more detail, we could see that one's been decreased. So I was actually very happy in terms of stability, and that's actually got some really important ramifications in terms of actually thinking about 2D NMR data, where you might need to use more and more scans because you may not be using basically concentrated solutions, and therefore you might need bigger time acquisitions to get good quality spectra. In terms of actually getting some 2D spectra using fluorine, I've got an example here of some fluorine proton cozy. We can see the actual effect of why we might want to use fluorine, because if you look in the F2 direction, we can see the 2 CH2s and how close again they are in terms of chemical shift. And we can also see how nicely resolved the 2 fluorine 19 environments are in the F1. Now, this is, I quite happily admit, this is not the best quality spectrum I can collect. I know I can collect better, and that was because I made the mistake as the experimenter to actually use too wide a window in the F1 direction. So I could have significantly narrowed that down, and I would have actually got better peak resolution than what we have here. But as whatever with these kind of things, it's all about experimentation, improving, and I'm quite happy to say that not all the time I get things right. But I just wanted to put this up to basically exemplify the kind of data you can get. And again, basically say that it's not just limited to proton, we can certainly involve other nuclei such as fluorine. And I'm going to finish up by just showing you some carbon-13 data. And this is something I really think the flow system can be massively helpful in terms of relaxation. So again, just because I wanted to keep things fairly succinct in what I was basically trying to explore with you today, is we're looking at this reaction here. So this is the same reaction that we're looking at, and this data was collected right near the start, so we can't actually see really any of the ester product in terms of the carbon, because the equilibrium is very much towards that of the starting reagents. And the thing about carbon is that carbon nuclei such as this quaternary carbon of the acetic acid have got very long T1s. They could be upwards of a minute, which means they've got a very long relaxation time. And that normally means their intensity in the carbon-13 NMR spectrum is very weak. Now, normally we can get away with around that by using a smaller flip angle. So this is the flip angle in terms of excitation, whereby you might use something about 30 degrees. And we normally have to use quite a long relaxation time to enable that nucleus to relax fully in order to actually get the highest intensity we can. Because we're flowing, we don't really have to worry about relaxation, because anything that we're excited is then replenished by something that hasn't been excited. So we can actually drop down significantly the relaxation time when collecting these spectra. So all of these actual spectra that I'm showing here on the screen were all collected using a 90-degree pulse and the relaxation time of only a second. And if I just go through the spectra now with you, so we've got the quaternary peak is here at about 160 ppm. We've then got the carbon, which has got the 3 fluorines attached to it of the 2,2,2 trifluoroethanol. So we can see the CF coupling here. We've then got the CH2 at 40 ppm that is next to CF3. And that shows up as a quartet because we see the splitting to the 3 fluorine atoms that are within 2 bonds of it. And then lastly, we've got the methyl group of acetic acid, which is here at about 0 ppm. Again, don't worry too much about the chemical shift. It's just a kind of arbitrary scale. I'm not saying exactly that's where the peaks will be coming, but they're just used as basically something to infer what is going on. Spectra 2 through 4 are a series of depth. So we've got the depth 45, the depth 90, and the depth 135, which are spectra 2 through 4 respectively. And the depths are quite useful in terms of actually doing structural elucidation. In this case, we actually know what the molecules are, but you might be actually studying a reaction whereby you're doing it for the first time, you don't really know what's going on. You might want to get this kind of data to explore the product or products that are being produced from your reaction. So we can see that we're actually being able to selectively sort these carbon nuclei based on the number of proton environments they've got associated with them. Particularly if we look at spectrum 3 here, which is the depth 90, we don't see any peaks there because we haven't got any CH environments in either of those 2 starting materials. And also in the depth 135, we can see that the CH2 environment is pointing downwards in emission, whereas the CH3 is pointing upwards in absorption. So we've got that difference there, and that is exactly what we'd expect if we was to look at this system on a theoretical basis in terms of what we'd expect for that spectrum. So I hope you've enjoyed the presentation that James and I have put together. I have largely wanted to basically explore with you today the kind of reactions that you can do. I didn't want to be exhaustive in my approach. I'm not an organic chemist by trade, I'm an inorganic chemist, but really I wanted to basically give you something that would hopefully get you excited about Flow NMR and possibly get you thinking about what you're doing. So James today has told us about a new benchtop NMR system called XPulse. He's told you about the customizable configurations, which is incorporated Flow NMR and variable temperature. And also told you about the Broadband XPod that allows you to look at phosphorus to silicon and along with other nuclei on that system. I've been largely telling you about the flow cell with the external lock and how you can use that to monitor some reactions, and particularly the esterification reactions. And for that, you can actually get some information about the reaction dynamics. I've also shown you about how we can calculate some key reaction parameters, such as Gibbs free energy, enthalpy, and entropy. And I've also explored the actual stability in terms of actually collecting data over a long period of time, which may be required if you're looking at a particularly slow-moving reaction in terms of completion. So I'd now like to hand over to you guys. Hopefully you've got loads of questions to ask. Oxford Instruments have got their email address there, so please do contact them if you've got any other questions to ask.
Fantastic. Thank you very much, Ryan, and thank you to James as well. Looking at the questions that have come in, I think we could potentially run an entire webinar just on the setup of a Flow NMR system, as we've had a number of questions come through about that. So let's kick off with that, which feels like it might be open to both of you. So we'll make sure that James's microphone is live as well. The question for me is where to start. We've had so many. So let's pick one from, let's go with Dimitris first. Dimitris wants to know what the volume is of the flow cell, so the active volume, the volume that's inside the detection of the coils. What sort of volumes are we looking at? So
the flow cell in its entirety has a volume of just short of 2 milliliters. However, that 2 milliliters has to go through obviously the entirety of the instrument, or the majority of it at least. And the amount of material inside the detection coil is a small proportion of that. Roughly, let me try to do the calculation off the top of my head here, but
sorry, didn't mean to put you on the spot and make you do some mental arithmetic.
It's fine. But it is a small fraction of that in the sort of microliter type range. But the one thing that I think that our instrument and the setup that we have does do is that because we have the external lock, that means you don't have to have the deuterated solvents in the system, which and in the reaction mixture, which means that you have more of the compound that you're actually interested in, and you're not tainting it, spiking it with those deuterated solvents. But also it means that the actual compound, because of our magnet design, stays in the field longer than it would for other instruments. That means that you have a more chance of polarizing the molecule as it flows through the cell, so you get a larger signal when it's actually in the active region itself. Ryan did show quite nicely how, with increasing flow rate, that sensitivity, or that signal that you can produce, does decrease, because you don't have the time to polarize the sample.
Thank you very much. Again, lots of questions on the technicalities there. So following on from that, we've had a question from Daniel Taylor, who asked how fast you really can flow the reaction through the machine. So clearly you showed that as you increase the flow rate, you do lose some acuity in your results. But what do you think the limits really are, and still getting usable numbers?
So I'll answer that question. So there is actually kind of a hardware consideration there, which is actually linked to the peristaltic pump. So the quicker you try and flow the liquid around the system, it tends to generate a bit more back pressure. I only went up to 10 mil per minute, mainly because it just seemed to me to be a nice place to stop. But at that point, there was absolutely no back pressure being generated on the peristaltic pump that I'm using. It's got a nice digital readout that tells me about this. So in order to actually give Daniel a full answer to his question, I don't actually know. I've only gone up as high as 10 mil per minute. I don't really know what the limit could be. I've not really wanted to push it beyond that. But really, at 10 mil per minute, I was not unduly worried at all about going any higher. It's just the fact that I had no real reason at that point to actually push it any more than that. So certainly something for me to go away and actually explore.
Well, that leads us very nicely to one of a few questions from Chris Thompson. Now, Chris, I recommend that clearly you're very engaged in this. It's obviously something you've got a bit of experience with already. That email on the screen will probably be able to provide you answers to all of your questions. But the one that is particularly relevant right now is Chris has asked how secure the connections are in your flow cell. So can it be used under back pressure? And if so, what sort of pressures are we looking at?
So I'll start this and see if Ryan may want to add a comment. We use for the flow cell itself typical HPLC type connectors. We have never run the flow cell in a situation or at a flow rate where we are likely to generate a back pressure as yet. But as you said, Ben, if Chris has a specific question or a specific application in mind for that, we'd be more than happy to explore that with him and really understand what the limits are for flow NMR in our system.
Thanks very much. So yes, Chris, do please drop that email line, and they should be able to help you out with anything in particular you're looking at. Let's move away from the actual setup itself a bit. We've got a question. I mentioned earlier the current crop of undergraduates, and of course we promptly received a question from a current undergraduate. So he's saying that the lithium NMR is quite new, and does it require a particular internal standard, or is there any other way to quantify it?
So yes, obviously, I think the most accurate way to do the quantification would be to use an internal standard. However, a lot of the compounds, the mixtures that we have come across have been industrial type battery electrolytes, and therefore you don't necessarily want to have to spike the system with a internal standard. So what it is possible to do is that as long as you keep the settings for the spectrometer the same between measurements, you can generate yourself a calibration curve and then quantify against that curve to get you an accurate value for the quantity of lithium within your sample.
Thank you very much. That was from Xuanhang Zhang. So thank you very much for your question. Good luck with your degree as well. I hope that all goes well. You showed us some wonderful 2D experiments earlier, and we have had the question, can you only run that with protons and fluorine, or can you do 2D experiments with some of the other nuclei that we were discussing at the very beginning?
So with our system, you can run 2D experiments with any two of those nuclei that we described earlier. So typically anything that would be on the proton channel. So for us, the proton channel is also the fluorine channel, and anything on the X channel, which is anything from 29 silicon to 31 phosphorus, you can run most 2D experiments.
Thank you very much. I think we are rapidly running out of time. We've had a couple of comments about the magnet temperature. So again, Chris Thompson was wondering what temperature the magnet runs at. Andrew Hall asked more specifically, given that the magnet temperature is fixed, does that mean that the sample is at a different temperature in the cell than it is in the reactor?
So I think that, well, Ryan, do you want to have a discuss your particular setup here, and then I could maybe discuss the generality?
Yeah. So the temperature of the magnet, I think off the top of my head, is about 35 degrees Celsius. So you can measure that using an ethylene glycol sample. And I know for basically on the other part of the question, which is how when the liquid flows in there, about it being a different temperature, the rest of the reaction mixture, is that if you look at the ethylene glycol sample, it does take a period of time to actually bring itself up to the right temperature. So if you keep on looking at the same sample of ethylene glycol, you can see the actual temperature increase until it reaches a plateau. And that plateau takes about 8 to 10 minutes off the top of my head. So in terms of the reactions I'm looking at, I'm not going to say that there is no actual temperature increase whilst it's in there, but I think for the actual period of time that it is in there, it's actually quite minimal. So I hope that answers the question.
So I think that also, maybe I'll expand on that a bit, that one of the benefits of benchtop NMR is that you can put your system close to your reaction, which means that you don't have long lengths of tubing where the reaction or the reactants would change hugely in temperature, but those are always, or usually, unless you have some very well insulated tubing, going to have some effect on the temperature of the reactants. As Ryan rightly says, the temperature of the magnet is actually a little bit warmer than that, somewhere about 40 degrees, but the heating effect is minimal. One thing that, again, one of the other questions in here that I had a quick look at said was depending on the flow rate, does it destabilize the magnet if your reactants are at a different temperature to the magnet itself? Well, one of the things that our system has is that we have a very different magnet design to a lot of the other benchtop systems out there, and one of the bonuses of that for flow chemistry and reactions like this is that we have a much larger thermal mass. So typically in the range of temperatures that we have measured so far, we've seen no destabilizing effect of flowing warm or hot reactant mixtures through the magnet at any of the flow rates that we've discussed so far today.
Fantastic. Well, I'm afraid we are going to have to call things to a halt as we have unfortunately run out of time. I'd like to say a huge thank you to James and Ryan for joining us today. It's been a fascinating presentation. Clearly, with anything with this number of questions, there's still a lot more that can be said about this. So thank you ever so much to Oxford Instruments for opening our eyes to this and finding the right people to tell us about such a fascinating area. Now, as we said at the beginning, this entire thing will be recorded, and everybody who attended will be sent a copy of the recording. You'll easily be able to come back and watch that. If there was anything you missed or anything you wanted to watch again, that will be available in the next couple of days. You'll receive an email with that, along with your certificate of participation, which you'll receive as a thank you for being here live during the presentation itself. If there are any other topics that you would like Chemistry World webinars to cover, then please drop us a line, cwwebinars@rsc.org, and we'll be very keen to try and find out the sorts of things that the chemistry community wants more of these interactive presentations, Q&A sessions about. So do drop us a line if there's anything that you think you'd like to know more about. I'm Ben Valsler, Chemistry World's digital editor. I'd like to thank you all once again for all of your excellent questions, and thank you for giving us your time for this Chemistry World webinar. We'll be back with another Chemistry World webinar very soon.